Hello friends, welcome back to the Control System Simplified series. Today we'll discuss about time response analysis of first order system. If we consider the following block diagram of the closed loop control system, there is an open loop transfer function of 1 by st, which is connected with a unity negative feedback. This is what so when there is no gain given here, we have to consider that it is unity gain. It's a unity gain negative feedback. So this block is connected, the output is connected with a unity. This is the typical control system that we are considering here. Now we know that the transfer function of the closed loop control system has unity negative feedback as C of S by R of S is equal to G of S by 1 plus G of S. This we have already seen. Now, in this, let us substitute this G of S this is G of S for this transfer function, gain. So, let's substitute G of S is equal to 1 by ST in this equation. We get C of S by R of S is equal to 1 by ST by 1 by 1 plus 1 by ST. That gives 1 by ST plus 1. Okay, that's the simple term. So the power of S is 1 in the denominator term. Hence, this transfer function is of first order type and is said to be the first order system. So the transfer function for this is equal to C of S by R of S is equal to 1 by ST plus 1. So the power of this S will give us the order of the system. So if we want to have an output, C of S is equal to 1 by ST plus 1 into R of S. That will be the thing where C of S represents the Laplace transformation of the output signal of C of t, and R of S represents the Laplace transformation of the input signal R of t. And capital T is the time constant. Now, the following steps are to be followed in order to get the response, that is output response of the first order system in the time domain. The first one is take the Laplace transform of the Laplace transform of the input signal R of t. Then consider the equation C of S is equal to 1 by ST plus 1 into R of S. This is the output of this. Substitute R of S, whatever is the input for different test signals, ramp, step, impulse, parabolic input signal. Substitute the corresponding RS of that signal. Then do partial equations of C of S if required. And then finally apply inverse Laplace transform to get from the C of S. Then you get C of t input in time domain. So earlier we have seen the standard test signals like impulse, step, ramp, and parabolic. Now let's consider to find the response of the first order system for each of the input one by one. Okay, now we are taking here is the impulse response of the first order system. If we consider the unit impulse signal as an input to the first order system, R of t is equal to delta of t. If we apply the Laplace transformations on both sides with R of S is equal to, we get R of S is equal to 1. Now, if you consider this equation, C of S is equal to 1 by ST into R of S. This is a standard transfer function that we have seen. Now we are applying R of S is equal to 1 into this. Because R of S is equal to 1, if we take the Laplace transformation of delta of t. Okay. So if we substitute this, then we get 1 by ST plus 1 only. Then if we rearrange the above equation in this, we get C of S is equal to 1 by t into S plus 1 by t. Because S we should always keep without any coefficient. So that gives C of S is equal to 1 by t into S plus 1 by t. So if we apply the inverse Laplace transformation on both sides, then we have 1 by t e power minus t by tau. Okay, u of t. This is when we apply the inverse Laplace transform. So we get the output C of t in time domain as 1 by t into e power minus t by tau into u of t. Capital T is the time constant Here, small t is the time. Small t is the time and capital T is the time constant. Here you will see this is varying from this. So this is the C of t is always given as, initially it is at 1 by t, and this is the transient decaying function as t tends to infinity. That is the impulse response of the first order system. Now let's see the step response of the first order system. If we give the unit step signal as an input to the first order system, R of t is equal to U of t. Okay, same thing if you take U of t, if you take the Laplace transform, you get R of s is equal to 1 by s. This is the Laplace equation for U of t equivalent. Now if you say, consider the same old equation, C of s is equal to 1 by st plus 1, and substitute 1 by s and arrange this as we did earlier. 1 by C of s is equal to 1 by st plus 1 into 1 by s. Here we are getting a different form. So 1 by s into st plus 1. So if we do the partial fractions, partial fractions of CS that we need to remember, that 1 by s into st plus 1, we get a by s plus b by st plus 1. So this gives 1 by s into st plus 1 is equal to a into st plus 1 plus b into s divided by s into st plus 1. So you have denominator, we have same. So we are equating only the numerators. So we get a into st plus 1 plus bs is equal to 1. So by equating the constant terms on both the sides, we will get a is equal to 1, because we are only because AST here plus A plus BS. So if we equate only the constant terms, A equals 1. So if we substitute A is equal to 1 in this, we get 0 is equal to, on both sides, coefficient of S terms only we are equating. Okay. So here there is no coefficient of S term. So 0. Here coefficient of S term, A being 1, coefficient of S term is T. So T we have. And here coefficient of S term is B. So T plus B is equal to B. B is equal to minus T. Okay. So if we substitute A is equal to 1 and B is equal to minus T in partial expansion of this equation, so we get 1 by S minus T by ST plus 1, that equal to 1 by S minus T by T into S plus 1 by T. Because if we have to apply inverse Laplace transform, we have to get it into, there should not be any coefficient for S. Okay. So ultimately we get C of S is equal to 1 by S minus 1 by S plus 1 by tau. If we apply inverse Laplace transformation on both sides, we get time domain C of t output is equal to 1 minus e power minus t by tau into u of t. If we expand this, you will get ut minus u of t into e power minus t by tau. So in this equation, e power minus t by tau is the transient, and after this it is ut. This is the input signal. So this color thing is C of t, and this dotted line is input, u of t. Okay, so finally we get the response as, this is the transient response, e power minus t by tau, plus after this time, this is a transient, then after this you have steady state, that is nothing but u of t. So that's the response of the first order system for unit step response. Then if you see the ramp response of a first order system, taking unit ramp signal as input to the first order system, R of t is equal to t into u of t. This is the unit ramp signal. So if we take Laplace transform, we get R of s is equal to 1 by s square we get. Now consider the same earlier equation, C of s is equal to 1 by s t with R of s, and substitute R of s is equal to 1 by s square. In this equation, we get C of s is equal to 1 by st plus 1 into 1 by s square. That is equal to 1 by s square into st plus 1. Now, if we do the partial fractions of C of s for this 1 by s square into st plus 1, we get a by s square plus b by s plus c by st plus 1. Now, similarly, substituting and equating the coefficient of s square terms on both sides, you will get c is equal to t square. right? And as usual, earlier we get, you do it, we will get A is equal to 1, B is equal to minus T, and C is equal to T square. Okay, in partial fraction expansion of CS. So if we substitute this in C of S, we get 1 by S square minus T by S plus T square by ST plus 1. That is equal to 1 by S square minus T by S plus T square by T if we take out S plus 1 by T. Okay, we get C of S is equal to 1 by S square minus T by S plus T by S plus 1 by T. So this T and T square goes, so T by 1 plus S plus 1 by T. Because if you want to take the inverse Laplace transform, so S coefficient of S should always be 1. That's why we will convert this into this equation. So when you apply the inverse Laplace transformation on both sides, we get C of T is equal to T minus T e power plus T into e power minus T by tau into U of T, right? And that's exactly what we get. So if we get the transfer function of T is equal to T into e power minus T by tau into U of T. Okay, so this is the ramp response, and this is how the output response. This is the input, and this is the equation of C of T, what we are seeing here. So up to this function, you will have the transient response is capital T into e power minus T by tau multiplied by U of T. And from this onwards, you will have T minus T into U of T. This is the standard thing. There will always be a time lag here, what we have seen, right? So that's exactly about the unit step response. Then parabolic step response of first order, if you take, it will be the input of the first order system, R of T is equal to T square by 2 into U of T. Okay, that's the equation. So if you do the apply Laplace transform on both sides, you get RF S is equal to 1 by S cube. Do the same thing. So RF, by substituting RF S is equal to 1 by S cube, we get 1 by S cube into ST plus 1 here. Then if you do the partial fractions, same A by S cube plus B by S square plus C by S plus D by ST plus 1. This is how we get. And the same in earlier fashion, if we calculate, we get same thing, T minus T plus T square minus T square by S plus 1 by T. If we apply inverse Laplace transform on both sides, C of T is equal to T square by 2 minus capital T small t, capital T square minus capital T square into e power minus T by tau into U of T. So the unit parabolic response C of T has both the transient and steady state term. So the transient term is nothing but minus T square into e power minus T by tau ut. And this entire thing is into ut is the steady state response. That's the response of the unit parabolic system. So from these responses, we can conclude that the first order control systems are not stable with the ramp and parabolic inputs because these responses go on increasing even at infinite amount of time. The first order control systems are stable with impulse and step inputs because these responses have bounded output. But the impulse response doesn't have steady state stuff. So the step signal only is widely used in the time domain for analyzing the control system from their responses. So that's exactly about the time response analysis of the first order system. Thank you very much.